integral using a fast, visual substitution cue. The goal is to evaluate the integral from 0 to infinity of x times e to the negative x squared, dx. Step 1. Rewrite as a limit because the upper bound is infinity. The integral from 0 to infinity equals the limit as r goes to infinity of the integral from 0 to r of x e to the negative x squared, dx. Step 2. Spot the quick visual cue. Inside the exponent we have x squared, and out front we have x dx. That is perfect for the substitution u equals x squared. So let u equal x squared. And then du equals 2x dx, which gives x dx equals 1/2 du. When x equals 0, u equals 0. When x equals r, u equals r squared. Therefore, the integral from 0 to r of x e to the negative x squared dx becomes 1/2 times the integral from 0 to r squared of e to the negative u du. Step 3. Integrate the exponential. The antiderivative of e to the negative u is negative e to the negative u. So we have 1/2 times bracket negative e to the negative u evaluated from 0 to r squared. This simplifies to 1/2 times the quantity 1 minus e to the negative r squared. Step 4. Take the limit as r goes to infinity. Because e to the negative r squared goes to 0 very fast. The limit becomes 1/2 times 1, which is 1/2. Therefore, the value of the improper integral is 1/2. Now, the quick intuition. Match x squared in the exponent with x dx in front using u equals x squared. That collapses the integral to a simple exponential with total area from 0 to infinity of 1, and the factor of 1/2 remains.
Method. Find the volume formed by revolving the region bounded by y equals x squared, y equals 0, and x equals 2 about the x-axis. Step 1. Sketch and visualize. Draw axes and label tick marks. Plot the parabola y equals x squared. Mark the vertical boundary x equals 2. Shade the region between the curve and the x-axis from 0 to 2. When this region spins around the x-axis, it creates a bowl-shaped solid. Step 2. Set up a typical cross-section. At some x value, take a thin slice perpendicular to the x-axis. Its height is y, which equals x squared. When the slice revolves around the x-axis, it forms a solid disk. So the radius r of the disk at position x equals x squared, and the inner radius is 0. The area of that disk is pi times r squared, which becomes pi times x to the 4th. We will use this cross-sectional area in our volume integral. Step 3. Write the volume integral. We add up all of those disk areas from x equals 0 to x equals 2. So the volume equals the integral from 0 to 2 of pi times x to the 4th, dx. Step 4. Compute the integral. The antiderivative of x to the 4th is x to the 5th over 5. Evaluate from 0 to 2 to get 32 over 5. Multiply by pi to get the final volume.
X squared. Step 1. Find their intersection points by setting the equations equal. X squared equals 4x minus x squared. Move everything to one side. 2x squared minus 4x equals 0. Factor. 2x times x minus 2 equals 0. So the solutions are x equals 0 and x equals 2. Step 2. Decide which curve is on top between 0 and 2. Consider the difference. Left parenthesis 4x minus x squared, right parenthesis minus x squared equals 4x minus 2x squared. On the interval from 0 to 2, this expression is positive. So the upper curve is y equals 4x minus x squared, and the lower curve is y equals x squared. Step 3. Set up the area integral. Area equals the integral from 0 to 2 of upper minus lower. That is the integral from 0 to 2 of 4x minus 2x squared, dx. Step 4. Integrate and evaluate. An antiderivative is 2x squared minus 2/3 x cubed. Evaluating from 0 to 2 gives 8 minus 16 over 3. Therefore, the area equals 8 over 3 square units. Find dy dx for the equation sign of x, y equals x squared plus y. We'll proceed step by step, and I will highlight each move as we go. Step 1. Differentiate both sides with respect to x. On the left, we write d by dx of sine of x, y equals. On the right, d by dx of x squared plus y. For the left side, we use the chain rule. The outer derivative of sine is cosine, and the inner derivative of x, y uses the product rule. That's x times d, y dx plus y. The right side is straightforward. The derivative of x squared is 2x, and the derivative of y is dy dx. Putting this together gives cosine of xy times the quantity x dy dx plus y equals 2x plus dy dx. Step 2. Expand and collect the dy dx terms. We distribute the cosine term to get x cosine of xy times dy dx plus y cosine of x, y equals 2x plus dy dx. Bring all dy dx terms to the left, and constants to the right. X cosine of xy dy dx minus dy dx equals 2x minus y cosine of xy. Now factor out dy dx. The bracket x cosine of x, y minus 1 times dy dx equals 2x minus y cosine of xy. Step 3. Solve for dy dx by dividing both sides by the bracket term. Dy dx equals the fraction 2x minus y times cosine of xy over x times cosine of xy minus 1. That is our result. Recap. Chain rule on sine of xy, product rule on xy, collect dy dx terms, factor, and divide. Every step shown gives a quick visual path to the answer. In this lesson, we will evaluate a single integral step by step with clean algebra and a helpful substitution. Here is the integral. The integral of x cubed over the quantity x squared plus 1 squared with respect to x. Notice the repeated quantity x squared plus 1 in the denominator. To simplify, let u equals x squared plus 1, so that du equals 2x dx. This substitution matches the highlighted denominator. Next, we rewrite the numerator to include the piece x dx. X cubed dx equals x squared times x dx. But x squared is u minus 1, and x dx is 1/2 du. Therefore, x cubed dx equals parenthesis u minus 1 parenthesis times du over 2. Now substitute everything into the integral. The denominator becomes u squared, and the numerator becomes parenthesis u minus 1 parenthesis times du over 2. So the integral equals 1/2 times the integral of quantity u over u squared minus 1 over u squared du. This simplifies to 1/2 times the integral of 1 over u minus 1 over u squared du. Integrate term by term. The integral of 1 over u is the natural log of the absolute value of u. The integral of negative 1 over u squared is plus 1 over u. Altogether we get 1/2 times bracket natural log absolute u plus 1 over u bracket plus c. Finally, substitute back u equals x squared plus 1. The result is 1/2 times the natural log of x squared plus 1, plus 1 divided by 2 times the quantity x squared plus 1, plus c. That is the complete evaluation, shown with a clear substitution and clean algebra. Iterated once, and keep the visual steps perfectly aligned. The problem is, evaluate the indefinite integral of e to the x times sine x dx. First, recall the integration by parts formula. The integral of u dv equals uv minus the integral of v du. Now, first pass. Choose u equals sine x, and dv equals e to the x dx. Then du equals cosine x dx, and v equals e to the x. Apply the formula to get the integral of e to the x sine x dx equals e to the x sine x minus the integral of e to the x cosine x dx. We still need that remaining integral. Compute the integral of e to the x cosine x dx with integration by parts again. Choose u equals cosine x, and dv equals e to the x dx. Then du equals negative sine x dx, and v equals e to the x. So the integral of e to the x cosine x dx equals e to the x cosine x plus the integral of e to the x sine x dx. Now, we combine both results and solve. Let capital I be the integral of e to the x sine x dx. From the first pass, we have I equals e to the x sine x minus the integral of e to the x cosine x dx. From the second pass, the integral of e to the x cosine x dx equals e to the x cosine x plus I. Substitute this into the first equation to get I equals e to the x sine x minus e to the x cosine x minus I. Move terms to solve. 2I equals e to the x times quantity sine x minus cosine x. Therefore, I equals 1/2 e to the x times quantity sine x minus cosine x plus the constant c. We are done. The integral of e to the x times sine x dx equals 1/2 e to the x times sine x minus cosine x plus the constant c. Classic sliding ladder related rates problem with clean step-by-step cues. We'll define our variables. X of t is the distance from the wall to the foot of the ladder. Y of t is the height of the top of the ladder on the wall. The ladder length is 10 feet. We are told that dx by dt equals 1 foot per second. The foot is moving away. At the instant when x equals 6 feet, we want dy by dt, which will be negative because the top slides down. Step 1. Write the geometric relation using the Pythagorean theorem. X squared plus y squared equals 10 squared, which is 100. Step 2. Differentiate both sides with respect to time. Take d by dt of x squared plus y squared equals d by dt of 100. Using the chain rule, this becomes 2x times dx by dt plus 2, y times dy by dt equals 0. Step 3. Solve algebraically for dy by dt. First divide by 2. Move the x term to the other side. Now isolate dy by dt. We get negative x over y times dx by dt. Step 4. Plug in the known values, but first compute y at x equals 6. From the relation, y squared equals 100 minus x squared. Plug in x equals 6 to get y equals 8 feet. We also use dx by dt equals 1 foot per second. Step 5. Substitute and compute the rate. dy by dt equals negative x over y times dx by dt. Substitute x equals 6, y equals 8, and dx by dt equals 1. This equals negative 6 over 8, which is negative 3/4 feet per second. The negative sign tells us the top is moving down.
Part 2, also called the Leibniz rule. Differentiate the function f of x equals the integral from x squared to x of natural log of t dt. Throughout, assume x is positive so that natural log of x makes sense. Step 1. Recall the Leibniz rule. If big G of x equals the integral from of x to b of x of f of t dt, then the derivative g prime of x equals f of b of x times b prime of x minus f of x times a prime of x. Now, let's identify the pieces for our problem. Step 2. Plug into the formula exactly as written. F prime of x equals natural log of x times 1 minus natural log of x squared times 2x. We will simplify this next. Focus on natural log of x squared and the 2x. Step 3. Use the logarithm identity. Natural log of x squared equals 2 times natural log of x. Substitute that into our derivative to get f prime of x equals natural log of x minus 4x times natural log of x. Step 4. Factor the common term natural log of x. F prime of x equals natural log of x times left parenthesis 1 minus 4x right parenthesis. Final answer. The derivative equals natural log of x times 1 minus 4x.
Calculate the limit using a fast rationalizing trick with every step shown clearly. Here is the problem. Step 1. Write the limit cleanly. We will call it capital L. Step 2. Multiply by the conjugate to rationalize the numerator. We multiply and divide by square root of x squared plus 4x plus x. Step 3. Simplify the numerator exactly. The squared square root becomes x squared plus 4x, and the minus x squared cancels, leaving 4x. Step 4. Factor out x from the square root. We write square root of x squared plus 4x as absolute value of x times square root of 1 plus 4 over x. Since x goes to positive infinity, absolute x equals x. Therefore, the denominator becomes x times parentheses, square root of 1 plus 4 over x plus 1. The x cancels, giving 4 over square root of 1 plus 4 over x plus 1. Step 5. Take the limit. As x grows, 4 over x goes to 0. So the denominator becomes square root of 1 plus 0 plus 1, which is 2. The limit equals 2. Final answer, 2. We have a box with a square base and no top made from 108 square inches of material. The base side is x and the height is h. Find the dimensions that maximize the volume. Build a quick visual of the net. One square base accounts for x squared. For rectangular sides, each contribute x times h. Let's mark x along the base and h along a side. The surface area with no top is base plus 4 sides equals 108. So a equals x squared plus 4xh equals 108. Solve the constraint for h. 4xh equals 108 minus x squared. So h equals 108 minus x squared over 4x. This single formula ties height to x and will let us write volume as a function of x only. Volume equals base area times height. V equals x squared times h. Substitute h from the constraint. Simplify to v of x equals 1/4 times 108x minus x cubed. Differentiate to find the peak. V prime of x equals 1/4 times 108 minus 3x squared. Set v prime to 0 for critical points. That gives 3x squared equals 108, so x squared equals 36, and x equals 6, the positive solution. The second derivative is negative at x equals 6, so this critical point is a maximum. Now find the height from the constraint. H equals 108 minus 6 squared over 4 times 6, which is 72 over 24. So h equals 3 inches. The maximum volume is x squared, h equals 6 squared times 3 equals 108 cubic inches. Quick visual cue. The purple curve is the volume as a function of x. The peak at x equals 6 is the maximum. For steps, set up the area constraint, express h, write v of x, take the derivative, and solve v prime equals 0. Final dimensions. Base side 6 inches, height 3 inches. In this video, we will compute the integral of x squared over x squared minus 4 with respect to x. We will go step by step without skipping anything using polynomial division, partial fractions, and basic log rules. Step 1. Polynomial division. Because the numerator and denominator have the same degree, we divide x squared by x squared minus 4. This gives 1 plus 4 over x squared minus 4. We can justify it by writing x squared equals 1 times the divisor plus 4. Step 2. Split the integral. The integral becomes the integral of 1 with respect to x plus 4 times the integral of 1 over x squared minus 4. Step 3. Integrate the easy part. The integral of 1 with respect to x is simply x. We will carry the remaining piece for later. Step 4. Partial fractions. We write 1 over x squared minus 4 as 1 over x minus 2 times x plus 2. Set it equal to a over x minus 2 plus b over x plus 2. Clear denominators to get 1 equals a times x plus 2 plus b times x minus 2. Equate coefficients to obtain the system. A plus b equals 0 and 2a minus 2b equals 1. From a plus b equals 0, b equals negative a. Substitute to get 4a equals 1. So a equals 1/4. Then b equals negative 1/4. Now we rewrite the integrand using a and b. 1 over x squared minus 4 equals 1/4 times 1 over x minus 2 minus 1/4 times 1 over x plus 2. Therefore, the integral of 1 over x squared minus 4 is 1/4 times the natural log of the absolute value of x minus 2 minus 1/4 times the natural log of the absolute value of x plus 2 plus a constant. Multiplying by 4, because our split integral had a leading 4, we get natural log absolute value of x minus 2 minus natural log absolute value of x plus 2. Step 6. Combine all parts. The original integral equals x plus the log difference plus a constant. Using log rules, we can combine the logs into a single logarithm x plus the natural log of the absolute value of the fraction x minus 2 over x plus 2 plus c. Remember the domain restriction from the original integrand, x is not plus or minus 2. Final answer.
Thanks for watching Myverse Maths. If this helped you, hit that like button,
We will
drop a
evaluate
comment.
an integral using a clean trig substitution. Here is the integral. The integral of 1 over x times the square root of x squared minus 1 dx. Notice the pattern square root of x squared minus 1. Use the substitution x equals secant theta. Then dx equals secant theta times tangent theta, d theta. And the square root of x squared minus 1 becomes tangent theta. Now substitute everything. The integral becomes the integral of 1 over secant theta times tangent theta, multiplied by secant theta times tangent theta d theta. The common factors cancel, leaving simply the integral of d theta. This integrates immediately. We get theta plus c. Finally, convert theta back to x. Since x equals secant theta, theta equals arcsecant of x. Therefore, the integral equals arcsecant of x plus c. In this video, we will compute, step by step, the indefinite integral of arc cosine of x with respect to x, without skipping any steps. Our goal is to evaluate the integral of arc cosine of x dx. Step 1. Choose integration by parts. The formula says the integral of u dv equals uv minus the integral of v du. We pick u to be arc cosine of x and dv to be dx. Then we differentiate u and integrate dv. The derivative of arc cosine of x is negative 1 over square root of 1 minus x squared. So du equals negative 1 over square root of 1 minus x squared dx. And v is the integral of dx, which is x. Now substitute into the integration by parts formula the integral of arc cosine of x. Dx equals uv minus the integral of v du. That is x times arc cosine of x minus the integral of x times negative 1 over square root of 1 minus x squared dx. The two negatives make a plus, giving x times arc cosine of x plus the integral of x over square root of 1 minus x squared dx. Now we focus on the remaining integral. We evaluate the integral of x over square root of 1 minus x squared dx by substitution. Let t equal 1 minus x squared. Then dt equals negative 2x dx. So x dx equals negative 1/2 dt. Replace in the integral. It becomes negative 1/2 times the integral of t to the power negative 1/2 dt. Integrate. Negative 1/2 times 2 times t to the 1/2 equals negative square root of t. Back substitute t equals 1 minus x squared to get negative square root of 1 minus x squared. Finally, assemble the result. The integral of arc cosine of x. Dx equals x times arc cosine of x minus square root of 1 minus x squared plus the constant of integration. A brief note on the domain. For real values, arc cosine of x and the square root require x between negative 1 and 1. That completes our detailed, step-by-step solution.
Thanks for watching Myverse Maths. If this helped you, hit that like button, drop a comment, share it with your friends, and don't forget to subscribe for more quick maths tricks and proofs. The limit as x approaches pi over 2 of left parenthesis secant cubed x minus tangent cubed x right parenthesis divided by tangent x. We will show every algebra and limit step clearly. Step 1. Use a small angle substitution. Let t equal pi over 2 minus x. Then as x goes to pi over 2, t goes to 0. We have x equals pi over 2 minus t, so tangent of x equals tangent of pi over 2 minus t, which is cotangent t. Also, secant of x equals 1 over cosine x equals 1 over cosine of pi over 2 minus t, which is 1 over sine t, that is cosecant t. Therefore, secant cubed x becomes cosecant cubed t, tangent cubed x becomes cotangent cubed t, and the denominator tangent x becomes cotangent t. So the expression becomes left parenthesis cosecant cubed t minus cotangent cubed t right parenthesis over cotangent t. Step 2. Simplify algebraically using sine and cosine. Write cosecant cubed t as 1 over sine cubed t and cotangent cubed t as cosine cubed t over sine cubed t. Then the numerator becomes 1 minus cosine cubed t all over sine cubed t. Now divide by cotangent t, which is multiply by sine t over cosine t. We obtain the single fraction left parenthesis 1 minus cosine cubed t right parenthesis over left parenthesis sine squared t times cosine t right parenthesis. Step 3. Use small t expansions. As t goes to 0, cosine t equals 1 minus t squared over 2 plus higher order, and sine t equals t minus t cubed over 6 plus higher order. Compute cosine cubed t, that is approximately 1 minus 3t squared over 2 plus higher order. Therefore, 1 minus cosine cubed t is approximately 3t squared over 2 plus higher order. Also, sine squared t is approximately t squared, and cosine t is approximately 1. Substituting into the fraction, the numerator is about 3t squared over 2, and the denominator is about t squared times 1. So the ratio tends to 3/2. Step 4. Conclusion. The limit as x approaches pi over 2 of left parenthesis secant cubed x minus tangent cubed x right parenthesis over tangent x equals 3/2. Thanks for watching myverse Maths. If this helped you, hit that like button, drop a comment, share it with your friends, and don't forget to subscribe for more quick maths tricks and proofs. We will synchronize each algebra step to the narration for a crystal clear flow. Step 1. Write down the integral I equals the integral from 0 to pi over 2 of sine to the fourth of x over sine to the fourth of x plus cosine to the fourth of x dx. We will keep this expression in view as the target. Step 2. Introduce the complementary integral j. J equals the integral from 0 to pi over 2 of cosine to the fourth of x over the same denominator, sine to the fourth of x plus cosine to the fourth of x dx. Notice the denominators in I and j are identical. We'll box them to keep that visual cue. Step 3. Use the complementary angle substitution in j. Let u equal pi over 2 minus x. Then du equals negative dx. The limits flip. When x equals 0, u equals pi over 2, and when x equals pi over 2, u equals 0. Rewriting j gives the integral from u equals pi over 2 down to u equals 0 of cosine to the fourth of open parenthesis pi over 2 minus u close parenthesis over sine to the fourth of open parenthesis pi over 2 minus u close parenthesis plus cosine to the fourth of open parenthesis pi over 2 minus u close parenthesis times negative du. Using the cofunction identities, cosine of pi over 2 minus u equals sine u, and sine of pi over 2 minus u equals cosine u. Therefore, j becomes the integral from 0 to pi over 2 of sine to the fourth of u over cosine to the fourth of u plus sine to the fourth of u du, which is exactly I. So j equals I. Step 4. Add the two integrals. I plus j equals the integral from 0 to pi over 2 of sine to the fourth of x over the common denominator plus cosine to the fourth of x over the same denominator. Combine the fractions. The numerator becomes sine to the fourth of x plus cosine to the fourth of x over the same denominator. That simplifies to 1. Therefore, the integral of 1 from 0 to pi over 2 equals pi over 2. Step 5. Use j equals I to finish. Since j equals I, we have 2 I equals pi over 2. Divide both sides by 2, I equals pi over 4. That is the exact value of the original integral. X approaches 0 of left parenthesis sign, x minus x right parenthesis, over x cubed. We'll solve it twice, first by repeated L'Hospital's rule, then by a Taylor series visual cue. First, check the form. X equals 0, sinus 0 minus 0 equals 0. And 0 cubed equals 0. So we have 0 over 0, an indeterminate form. We may use L'Hospital's rule. Method 1. Repeated L'Hospital's rule. Start with the original fraction. Differentiate top and bottom once. It's still 0 over 0. Differentiate again. Still 0 over 0. Differentiate a third time to clear the indeterminacy. Now plug in x equals 0. We get negative 1 over 6. Method 2, Taylor series visual cue. Sine x equals x minus x cubed over 6 plus x to the fifth over 120 and higher powers. Subtract x to form sine x minus x. The x terms cancel, leaving negative x cubed over 6 plus higher order terms. Divide by x cubed. We get negative 1 over 6 plus a term of order x squared. As x approaches 0, that small term goes to 0. So the limit is negative 1 over 6, matching our first method. Both pathways agree. The answer is negative 1/6. L. Hospital's rule shows the mechanics, while the Taylor series gives a fast visual cue by exposing the leading term.
Trigonometric limit using a fast visual cue. Evaluate the limit as x approaches 0 of open parenthesis 1 minus cosine x close parenthesis divided by x squared. Step 1. Use the half-angle identity. Cosine x equals 1 minus 2 sine squared of x over 2. Rearranging 1 minus cosine x equals 2 sine squared of x over 2. Step 2. Substitute this directly into the limit. Step 3. Factor out the constant 2 and think of sine squared as a square. Step 4. Match the famous limit sign, u over u, by letting u equal x over 2. Then sine of x over 2 divided by x equals 1/2 times sine u over u. Squaring gives 1/4 times sine u over u squared. Step 5. Use the standard limit. The limit as u approaches 0 of sine u over u equals 1. Therefore, our limit equals 2 times 1/4 times 1 squared, which simplifies to 1/2. Visual cue recap. 1 minus cosine x becomes 2 sine squared of x over 2. Then sine of x over 2 over x becomes 1/2 times sine u over u. The famous limit gives 1, and the constants multiply to 1/2. Goal is to evaluate the integral. The integrand is e to the 3x multiplied by sine of 2x. Recall the standard identity. The denominator is a squared plus b squared, and the factor in parentheses is a times sine of bx minus b times cosine of bx. Compare with our integral. Here a equals 3, and b equals 2. Substitute these values into the identity. Now simplify the denominator. 3 squared plus 2 squared equals 13. That gives our simplified antiderivative. Result complete.
Integral. Make the substitution. U equals cosine x, so du equals negative sine x dx. This pairs the sine x in the numerator with du. Convert the limits. When x equals 0, u equals 1. When x equals pi over 2, u equals 0. Rewrite the integral in terms of u. Now flip the limits to remove the minus sign. Recognize the antiderivative. The derivative of arctangent u is 1 over 1 plus u squared. Evaluate at the bounds. So the value of the integral equals pi over 4. Thank you for watching. Tap like, share, and comment, then follow and subscribe for more quick problem-solving tips. Let's make maths simple. One video at a time only on Myverse Maths.